Okay. Welcome to the webinar and the 4-hour webinar on nutrient management training, fertilizer manure calculations. My name is Dan Davidson, and I work with Illinois Soybean. I work with Illinois Soybean Association on behalf of ISA. I want to welcome you to this webinar. Today, this webinar is being presented by Dr. Bill Simmons, Professor Emeritus at the University of Illinois. He's still teaching agronomy classes there. Dr. Simmons has done a lot of work in things related to fertility, herbicide fade in the soil, and things like that. Pretty well known around Illinois. Just last week, he gave a seminar over the IFCA conference, and that was recorded, and it will be up on the Illinois Advisor website here early next week, or maybe by the weekend or early next week. So this webinar today is to help the participants prepare for the exam next week. This webinar is being recorded, and it will be posted by end of the day tomorrow on the Illinois Advisor website. As a CCA, you can apply for 1 credit. When you're registered, you will get 1 CEU in nutrient management, and if, for example, you listen to the recording of this, then you have to go to the CCA website and self-apply for a credit. Well, Dr. Simmons will present for maybe approximately 1 hour or so, go through his slides, and we'll be taking questions in. And when he gets done with his presentation, we'll present those questions to Dr. Simmons, and then we'll answer them. We'll kick this off here promptly, and we'll be done as soon as we get through the presentation and then all the questions. So that could be sometime between 11 a.m. and 11:30 this morning. Again, thank you for participating. On behalf of ISA, I welcome you here. And Dr. Simmons, I'll turn it over to you now.
Okay, thanks a lot, Dan. Hey, we'll go ahead and get started, everybody. Good morning to all of you. I'm sure I know some of you in person. I'm an emeritus professor, as Dan mentioned. It simply means that I get to come and go as I please and have no meetings to attend, which is quite a delightful situation. I've taught introductory soil science not only here but at North Carolina State University and Oregon State years past, and I'm currently teaching the introduction to crop science, so I'm having a lot of fun with that. Look forward to trying to help you out here a little bit. What we're going to do today is really try to break down calculations, how to approach calculations, some of the things you should be thinking about as you go into this certification exam. So really, I mean, there'll be some material here that everybody can use, I hope, and kind of a review, look at ways to approach problems, but it's primarily going to be focused on those folks that are taking the certification exam. And really the exam, from what we can gather, now I did not write the exam nor have I seen it, but from what we can gather, it really is going to emphasize a lot of scenario thinking. So at this elevated level of CCA training and performance, you'll be asked to kind of weave some concepts together, make some good decisions, good management decisions, use data in some cases to go ahead and make prescriptions or make recommendations for fertility using either fertilizer or manure. So, I've always said the best way to do well in an exam is to come in well rested and panic free. We're also going to teach you how to flip fractions and do some other math tricks. I put the Statue of Liberty up here too to signify our beckoning, welcoming arms for those coming in that are looking for care and feeding before the exam. So here are some of the things you, might be asked to calculate in this particular exam. There's going to be you're almost certain to see some kind of manure type calculations. And primarily what they're going to want to know is if you have the ability to look at the total output of a livestock system on an annual basis, kind of determine the amount of nutrients that are in that manure, and find enough land and suitable land to land apply that manure, get the greatest efficiency out of it, and make sure that you don't over-fertilize. You'll be looking at how much nitrogen, phosphorus, and potassium can come out of that manure in 1 year. And also, I think there's a possibility you'll be asked to look at the contribution of manure in years 2 and 3 as well. You may be asked a little bit about cover crop nitrogen availability. This will come into play, particularly if we're taking credits coming in with corn or maybe even wheat after alfalfa, and in some cases soybean. We'll be looking at how to take nitrogen credits across a variety of sources. as well as phosphorus credits and potassium credits. I will tell you that it's probably the case in every test I've ever written in this area for college students and for other CC training approaches. The big focus will be on nitrogen and phosphorus. They're the ones that have environmental interest. And of course, the nitrogen has a lot of different forms that it can be and a lot of different transformations that occur within the soil environment. You are going to have to likely take NP and K credits from previous fertilizer applications. You may see scenarios, particularly in more arid regions of the Corn Belt as we move west, where you're taking a pre-side dress nitrate test or other soil test to try to zero in on coordinating the correct amount and source of nitrogen, and also the credits from biosolids. In some cases, you may be asked to look at a municipal sewage sludge application and get some data on that and make the calculations on how many gallons or tons of that material would be applied and how much nutrition they would bring. It's not outside the realm of possibility that you'd be asked to look at analysis of irrigation water. Again, particularly producers in the western Corn Belt, where they have aquifers that have a fair amount of nitrogen within the water, you would take that as a credit, or to maybe look at wastewater. Okay, other fair game type deals here. Let's make sure I didn't miss anything. There we go. Other fair game calculations. The amount of NP and K amounts in fertilizer. And if we move down a couple lines, you'll see N-P2O5K2O and how that corresponds to the actual NP and K in fertilizer. We'll spend a little time talking about those different calculations. Also, you'll be asked to use different sources to meet certain needs. So you may have scenarios where it's wise to know, for instance, that urea should not be applied to high pH soils without some sort of urease enzyme inhibitor, or in fact cut into the soil, tilled in, or injected or knifed. So high pH soils, you're going to need to know to be careful about manure or urea applications where you may lose some of that nitrogen due to volatilization. You'll also be asked to convert parts per million of specific nutrients into pounds per acre. We'll go over that here this morning. And lime applications, I'm not sure if you'll see them, but that's another calculation that we're going to spend a little time with, of taking a lime requirement and looking at the type lime source that you have and making that connection, showing how much of your lime source is needed to meet a certain need as prescribed by a soil test. Other things, land needed for manure. I think this has been a topic that's been treated in this exam before. Looking at the livestock manure totals with a livestock operation and the nutrient load that comes with that. And then also, again, fertilizer amount by source. So we're hoping to, have this gentle teaching moment here where we're going to march together down this beautiful valley into the bathing light of truth. So math is fun. Here's Albert Einstein's pretty ramped up after putting a blackboard of material up there. The photo on the left is sort of shows a time and place when I thought, I can do some math. I did some graduate work at North Carolina State University, and the gentleman on the left is named Crip Smith, and the other guy is Mr. Ellis. And one day in the field, Mr. Crip said, "Bill, you're right good at ciphering," and I took that as a great compliment. So try to take the math and not get panic-stricken over it. So a little bit about the test. The test is written from performance objectives, and we've got all of these listed. You all have access to those. There's 50 or so multiple choice questions. Some of the folks who are taking the exam said there may be 55 or so. But the real key is really scenario type thinking. So within that context, you may be asked to use charts, graphs, do some interpretations, and really pull a number of things together. Your knowledge of fertilizer and your field knowledge and the soil type and the tillage and all these different things. And then you're also going to have to do some conversion factors. So again, 5 to 8 scenarios is what I heard, 7 to 10 questions for each scenario. And really, they're all going to be scenarios that will make you choose a particular management system, and the 4 R's on the source, the timing, the place, and amount will all be interwoven into these scenarios. So dealing with livestock waste is going to be one that you may see. Splitting nitrogen applications. Maybe you'll have an opportunity to discuss looking at nitrogen credits and then maybe using some fall anhydrous, but following that with some sort of side dress. So you'll have to do those calculations. Sandy soils with irrigation, you may be asked to put a smaller amount of nitrogen out and then put nitrogen with the irrigation water. Again, always looking at nitrogen credits and phosphorus credits. You may have sloping ground questions, which will bring into play use of manure. So manure, of course, we don't want to run off. You may have scenarios where you're looking at a series of fields within your farm that may be more or less suited for the application of manure. Right source on right location, so avoiding urea manure on high pH soils would be an example of that. Spoon feeding on irrigated sands. Talking about the fact that if you have no-till, it's generally a positive result, but you can have soluble phosphorus leaving no-till fields because of the fact or phosphorus reacts so well with soil particles, it doesn't move very deeply in the soil, and there's an enriched zone of phosphorus. So if you get water moving across that, it can take that out in the surface waters. You may have adjustments based on a pre-side dress nitrate test, or make adjustments to losses if you've had in-season denitrification and have to come back in with a side dress that was originally unplanned. You may have adjustments to carryover nutrients. So if we had a devastating drought and you had corn and no rainfall, you may take some credit for that nitrogen that's left. So all of these different scenarios are things you may have to look at. There's a nice little book that I obtained, and some of the folks that have taken this exam or our CCAs have spoken about this book, and it's a really neat sort of manual put out by the International Plant Nutrition Institute, and within that they have a number of scenarios. And actually, on my seminar or webinar Tuesday, I'm going to go sort of point to some things I think would be prime areas for testing. But this is the kind of thing you may be faced with or have to look at on this exam. So they may throw up a graph like this, and then you'll be asked to look for the economically optimal nitrogen rate, and you can see that's shown right there, where you come up and look at the intersection of the lines, and you've got higher organic matter soils needing less fertilizer. Seems contrary to some of the practices we've seen over the years. But in this particular case, you'd be putting 210 pounds out on the lighter soil and 180 out on the one with a little bit higher organic matter. So you might be faced with a scenario like this, and then asked to go in and sort of devise a system that will meet that amount of nitrogen. Okay, you may be asked to use manure. You may have a situation where you're taking credit for soybeans the year before, alfalfa, or some other thing. No-till high residue, this would trigger an idea on source where you go use a calculation. High residue, no-till, one of the big things there obviously is the use of UAN solutions or urea on the surface. They need to have a urease enzyme inhibitor with them, or need to be knifed in some way. Here's a big no-no that you'll likely be asked to weigh in on, so to speak. But we can't be applying manure to frozen ground, snow-covered ground, or ground that is saturated in the top 2 inches. So this is a practice that is not sustainable, not a best management practice. Okay, so that's just a fairly quick run-through on some of the things you might see, some of the ways you might want to approach this in terms of broad scenario thinking, bringing in all of your knowledge to make the correct decisions and mathematical calculations. All right. So, word on conversions. This is something that's sort of basic math once we wrap our head around it. An example of a conversion would be you're given pounds of something per acre and have to go ahead and convert that into kilograms per hectare, which are called SI units, and English would be the first ones, pounds per acre. And so you think broadly about how these conversions might be made. And I'll tell you frankly, I'm unaware of what sorts of actual factors you need to have in your brain when you go in there, but perhaps it'll even be provided. But the way that you would do this in real life, and you could have converting anything, a mass over an area, as the case is with the pounds per acre. You might have to convert mass per volume of liquid. I just wanted to get you kind of familiar with the process of how you move through using different factors, variables, fractions, whatever you want to call them, to arrive at the answer that you need. So in this case, if you're going from pounds to acre all the way to kilograms per hectare, you've got to have a relationship of the two measurements of mass in order to basically remove those terms from the original factor till we get to the last factor. All right, so there's a basic fundamental mathematical approach to this. If you have pound in the numerator, in the first one you want to get rid of it, and you eventually want kilogram in the numerator, you need to find the ratio of kilograms to pounds. And multiply that first one, since you have pound in the numerator and pound in the denominator, those two terms disappear, okay? You go down to the next one, kilograms per acre. Now we've got a mixed English and SI unit, and we're trying to get rid of acre. Acre is now in the denominator, so we need a term that has acre in the numerator, the top part. And again, those two cancel. Of course, there would be a constant that would be involved with each one of these, like how many kilograms per pound and so forth. But eventually you would work your way into kilograms per hectare. So with any sort of fraction, conversion factor, those are kind of the steps that you would take to get those done. Okay, on to the next one. And this is something that I would say has a high likelihood of popping up. And that is the conversion of essential element data from a soil test that are given in parts per million in some cases, and converting that into pounds per acre. And there's a neat little trick, or a reality I should say, that's out there that allows us to do this quite easily. So a part per million literally means that if you have 1 million, in this case, parts of soil or weight of soil, and you have one weight unit of that essential element, that is a part per million. But it's really handy that an average sort of bulk density of soil, you assume about a bulk density of about 1.3, and you look at what we call the acre furrow slice, which is about 6 2/3 inches deep. So that volume, 1 acre by 6 2/3 inches deep, weighs about 2 million pounds, okay? So now we're looking at how many parts per million are there in 2 million pounds. So we simply take the parts per million of that essential element, multiply it by 2, and it's converted directly to pounds per acre. So for instance, if you had 30 parts per million of phosphorus, you would have 60 pounds of phosphorus per acre. So that's a handy one to know. Fertilizer analysis. Okay, this is one that has baffled generations of soils and crop students at the university level, so we'll go through this here a little bit. The fertilizer analysis you see, like an 18460 would be an example, actually represents the amount of N, the P2O5 equivalent, and the K2O equivalent, okay? So people wonder, is there actually any P2O5 in that particular 18460? And the answer is no. This is a standard of expressing phosphorus that was developed probably hundreds of years ago when all of our elements were expressed as an oxide basis, okay? So the good news is the currency that we give soil tests and the amount of application we need uses this same unit, P2O5, K2O. So N is a percentage, and that never changes. So let's go through and take a look at what this means. So if you have a ton of 18460, that weighs 2,000 pounds, and you would multiply that by 18%, or 0.18, to get the amount of nitrogen in pounds that would be in a ton of 18460, right? So just doing this off the top of my head, this would be about 360 would be the number that's involved there. About 6% of that 2,000 pounds is going to be P2O5 equivalent. You can do the math on that, but it looks like it's about 920 pounds. Okay, so that's the way you would go through and calculate. So again, P2O5 and K2 are the way that these things are represented. Okay. All right. So another thing you might be asked to do, and this would be quite obvious that this would be something they would ask. You have a given fertilizer analysis, and then you have a given need for a certain amount of a fertilizer element. And then you may be asked to calculate the amount that you would need of these multiple sources that all provide, in this case, nitrogen. So, for instance, if you're using anhydrous 82% by weight, you would have to use more than 120 pounds because you're going to divide the 120 by 0.82 to get the pounds of anhydrous that you're going to use to meet that 120 pounds of nitrogen, okay? So another thing I like to tell students is think about this, step away from the math and don't vapor lock looking at the mathematics of this. Just at first, think about it this way. If you have a substance that is less than 100% of the nutrient that you need, it makes sense that you would need more of it than the weight of the nutrient that's required, okay? So if you're doing this math and you come up with less than 120 pounds of 8200, you know that you've made a mistake, all right? So 4600, that's going to be close to double the amount. It'll probably be somewhere in the area of, 230 pounds or something. You can do the math on that. But you divide by the decimal that's indicated by the number that's a percentage. So divide by 0.82, 0.46, or 0.30 to get the nitrogen. Okay, so that's what you're going to have to do there. And you may have to do that across a variety of fertilizer sources, including, several that are going to have multiple elements in them. Our diammonium phosphate, monoammonium phosphate would be prime examples of that. All right, this one is actually almost cruel and unusual. And I always tell students in my class, if you're not going for valedictorian, put your head down and close your eyes for this particular discussion because it can mess up your mind a little bit. But here's the deal. Since the fertilizer analysis is N, P2O5, and K2O, and we've already said there's no P2O5 or K2O actually in the bag, if you were asked specifically to convert to elemental N, P, and K, you would do it thusly. It turns out, if you take the molecular weight of phosphorus and oxygen, you add in 2 phosphorus molecules and 5 oxygen, and then you divide that into the weight of the 2 phosphorus, that entity, that P2O5, is about 44% phosphorus. So if you took some of these mythical P2O5 molecules, they would all be 44% phosphorus. K2O is 83% potassium, okay? So you would, to do calculations, converting to the elemental analysis, you would take the analysis of P2O5, for instance, and you would multiply it by 0.44, okay? So for instance, if you had 10, 10, 10, is N, P2O5, and K2O. If you expressed it as N, P, and K, it would be 10 for nitrogen. That remains the same. It'd be 4.4 for phosphorus and 8.3 for potassium. So that's how those calculations are done. Okay. So returning back to fertilizer calculations and some of the things that you need to be thinking about, particularly for this exam. The approach you take, which we'll go over here in a little bit, is pretty consistent in that you always want to look at your credits. If you have manure that has to be used, you need to do that calculation first. And then if you still need phosphorus, most commonly you're going to have a source, MAP or DAP, that are going to include nitrogen. So to do this, you got to be very careful. You have to make sure that you account for the nitrogen that is in these phosphorus sources. So let's say we still needed some phosphorus after all of our manure, or in some cases no manure, was there and our soil test indicated we needed phosphorus and we're using DAP or MAP. We do the calculation to figure out how much of that material we need. Then when we get the total amount of those fertilizers, we go back and multiply by the percent nitrogen that is in that fertilizer, and that will give us a positive quantity of nitrogen that we need to take as a credit. Okay, so let's say we're going to be asked to put together a comprehensive fertilizer program. And we're going to establish the need for nitrogen. That will come into play, okay? And so again, we have multiple sources we can use to meet that need. We want to credit the manure first and take credits for legumes, irrigation water, biosolids, or other things that are going to be added to that particular field scenario. If you still need phosphorus, then you do that next. Why do you always do phosphorus? After you've calculated the nitrogen need, but you haven't put any nitrogen out. We do the phosphorus calculation first because the phosphorus carrier invariably is going to include some nitrogen. Okay, so if incorrectly we did met the entire nitrogen need, and then we added DAP or MAP, we would actually be in excess of nitrogen because we had extra nitrogen with our phosphorus fertilization. Hope that makes sense to you. We need to take the credit from that phosphorus fertilizer and subtract that against the total amount of nitrogen that's needed in these scenarios. And then finally, you're going to select an appropriate nitrogen carrier if it's still needed. So how about establishing the need for nitrogen? And this has been kind of a moving target over the years, quite frankly. And I'm entering about my 30th year here at the University of Illinois. But one of the things that's happened fairly recently is within many of the Midwestern states, an approach used the maximum return to nitrogen has become the way to sort of figure out how much nitrogen needs to go out for an expected yield of corn. And that particular algorithm, I know that scientists at Illinois and perhaps Minnesota, certainly Iowa State, worked on that together. And basically, you don't really take the soybean credits into account per se, but whether you had your preceding crop, whether it be corn or soybean, is figured into this algorithm. And we'll look at one of these here in just a little bit. But if you go to the maximum return to nitrogen type approach, you don't take credit for soybeans directly. If, however, you are asked to make a calculation, and this is an older method that's been used and may still be used in some states, where you project a needed amount of nitrogen per expected bushel of corn. So years ago, Illinois had 1.2, some surrounding states had 1.1, some had 0.9. So let's say, as an example, 1 pound of nitrogen per expected bushel of corn. So using that method, you would take credit for soybean, and we'll take a look at those values here in a little bit. So for instance, if you have a field that's projected to yield 200 bushels, you would want 200 pounds of N in some form to go into that agronomic situation. You may have scenarios where your strategy for nitrogen application is adjusted mid-season by a pre-side dress nitrogen test. Okay, here's the example that I promised to show you on the MRTN, the maximum return to nitrogen. And I've just grabbed one scenario. You can go online and find this algorithm, and you're going to be asked the price of corn, the price of fertilizer, price of nitrogen basically, and whether you are following corn or soybeans and what your general location is. So this one, I believe, was central Illinois. And take a look there. I believe this one is following soybeans. I can't be certain. But anyway, you take a look, and the maximum return to nitrogen is right there in what's called the inflection point of that curve. So you take where that curve starts to bend down the other way and take that optimal thing right there. So that's the sweet spot for investment of nitrogen in terms of the maximum economic return. And you see that the gross return is the blue line above it. And you don't want to go to that one because what you're seeing there is, yes, we are getting a little more corn marginally with each additional addition of nitrogen beyond 184 pounds, but it's not economically satisfactory. In other words, you're not money on that. You're spending more money for nitrogen to get that yield, which is not paying off the cost of that nitrogen. So that'd be an example of a way to get into a nitrogen recommendation. So if you're looking at the static type approach, and you want to take a look at soybean credits, and typically I've seen 1 pound of nitrogen for every bushel of soybean yield up to 40, and I think in some cases they've used a limit of 50 bushels. So for instance, if you had a static recommendation of 200 pounds of N for corn, and the year before you had a 42 bushel soybean yield, which would make sense, it'd probably be much higher than that, let's say 70, you would still take 40 to 50 pounds of nitrogen credit and subtract that from the 200 total that you were looking at. Okay. Alfalfa, they may throw that in on you. If you come in behind alfalfa, you're going to get a minimum of 100 pounds of nitrogen the first year if you have a decent stand of alfalfa. And alfalfa will actually make contributions the second year. Now, everybody wants to know about these values, and here's a little disclaimer. These are the values that I have pulled out of various literature and bulletins from the universities around, primarily around the Midwest. You look at the alfalfa credits 2 years, manure up to 3 years, and the availability, from what I can tell, and I'm going to ask people about this before Tuesday, but 50% first year, 25% the second, and 10% the third year. So there is a continuing contribution of manure to the nitrogen pool in successive years. Okay, we'll spend a little bit of time with this. This conceptually shows the different areas you can be with soil testing. In other words, whatever the critical values can be. This is a generic chart that I've got, or figure, that shows a couple key levels, and then we'll talk about the strategies of what you do depending where your soil test falls on this particular line or figure. So here's the story. Soil tests have been done for years, but a couple hundred years ago there was no such thing. The soil test is really designed to get different values for different soils and then correlate those values with the response of additional fertilizer to additional yield. Okay? So in other words, if you have a very high soil test way out to the right side of this, that would indicate that the application of that specific fertilizer element would be unlikely to improve yields. All the way on the other side, a very low soil test value against standards would indicate you have an excellent chance of getting response to fertilizer. So if we're below the so-called critical level, if you look here at this little green area right here, and you'd be right, you'd be right in that sweet spot right here. Okay. That is the point, if your soil test that correlates with that right here, that would be the point at which you would start doing two approaches to fertilization. To the left of that circle of this line on the soil test, we are going to do two things. We're going to build up the soil, so try to improve the native fertility of that soil with fertilization, and we're also going to fertilize for the crops that are coming. So that would be either the year before the fertilization or 2 years after fertilization, because you may in some cases do a biennial fertilizer application ahead of corn and then not fertilize ahead of soybeans. So you may have that kind of a scenario. If you're way out here on this other side and you are up at this maintenance limit and you're past it to this direction, then that means you don't need fertilizer, okay? Because you've got a high enough soil test that crop is going to be fine without additional fertilizer. Okay, so if we take a look at the general philosophy of this, if you're below the critical value, you have two components to that fertilization. One is to build up the soil and also to maintain the crops that are coming in the next year or two. If you're between those 2 points, the critical value and the maintenance limit, you're going to fertilize for anticipated crop removal, and hopefully you'll get some kind of chart on that or table that you can derive numbers, and we'll take a look at an example here shortly. If you're over the maintenance limit, you are going to do drawdown, and there's not going to be an additional application of fertilizer. Well, here's an example, and this is out of the Illinois Agronomy Handbook. Some of these values change slightly depending what reference you use. But we're looking here at the amount of P2O5 and K2O. Remember, I told you we always use this currency, so this is handy. This relates directly to fertilizer. So for instance, for corn, if you look at the P2O5, in general, you're likely to pull off about 0.43 pounds of P2O5 per harvested bushel of corn. So if we do the math on this, let's say that we have a 200 bushel crop coming off, we're taking off 86 pounds of P2O5, all right? So hold that value in mind. And we're taking off 56 pounds of K2O. That would be 200 times 0.28. Okay. Soybean, let's say we're taking off a 60 bushel yield. You would multiply 60 by 0.85 and come up with the amount of P2O5 that's taken off that field by the soybean crop. Same thing with K2O, using the value 1.3 pounds per bushel. And the reason you would go through this, if you're asked to make a fertilization or meet a nutrient need in a 2-year rotation, starting with corn and then finishing with soybean, you could sum up the total amount of P2O5 and K2O that would be removed by those two crops. And then you can go back and start doing your fertilizer calculations, okay? So that would be, if you're in between that critical value and the maintenance limit, you're going to be using exclusively taking care of the crops that are coming off and the maintenance values. If, however, you're below the critical value, you're going to use the maintenance value that we just calculated with the crops that are coming off the field the next 2 years, but you're also going to be addressing a low soil test value. And the way that you take a look at that is to, again, this is out of the Illinois Agronomy Handbook, you'd use approximately 9 pounds of P2O5 to increase a soil test by 1 pound per acre over a 4-year period. Okay, 9 pounds P2O5 to bump it 1 pound per acre. So the annual rate, again, this is a strategy over 4 years. This is not all put out at one time. The annual rate per pound is 9 divided by the 4 years, or about 2.25 pounds of P2O5 each of the 4 years. Okay, that's how you would do that calculation. So let's say, for instance, you were at 20 pounds per acre and you want to go to 30. So that'd be 10 pounds per acre that you wanted to elevate that P test. And you're using 9 pounds for each pound. So that would be 90 pounds of P2O5 spread over a 4-year period. Okay. And so that's about 22.5 pounds of P2O5 per year. Okay. Hopefully you follow that. Similar approach with potassium, but the ratio is different. For potassium, you're going to use 4 pounds of K2O to increase the soil test by 1 pound over 4 years. So the annual rate is 4 pounds over 4 years, or 1 pound, and I should have changed that to K2O right there, but 1 pound of K2O for each of the following 4 years. Yeah, adding P2O5 to raise K2O is not going to be very helpful. All right, so that's some of the fertilizer calculations you might deal with. Let's go ahead and talk a little bit about manure. Now, manure, there are parts of Illinois, Indiana, Wisconsin, where manure is not a big player necessarily, and with limited livestock on some of the farming operations, but it's pretty big news in a lot of the Corn Belt. And manure is something it's a resource, it's an asset, but it has to be handled in an environmentally friendly way, and also taking full account of the nutrients that are in that manure. So, a couple sort of philosophical thoughts on manure. In some scenarios, you may be provided with laboratory data. The laboratory data may be on a dry basis, it might be on a wet basis. You might have to make some conversions and calculations depending on what form you're putting out in the field. And people always ask again about this availability of nitrogen in manure. And as near as I can tell, the consensus revolves around these numbers, that there's about 50% available the first year, 25% the second year, and 10% the third year, okay? But another big thing on manure is the phosphorus that it contains and the phosphorus loading that can occur. You know, many years ago in some farms, it probably wasn't uncommon to have the manure spread over the fields that were closest to the barn, and in some cases brought P levels up very high. But now we have to be careful to spread this manure around and put it in areas where it's going to be beneficial to raising the phosphorus amount without going over the top. So you have to look at the total amount of manure that's being produced on a given operation. And we'll talk a little bit about how you do that. Okay, meeting crop removal with manure. So you're always going to want to apply the manure before corn. That's typical, and the reason for that, of course, would be that because you have that 50% nitrogen availability in the first year, you want corn there to sort of slurp up that nitrogen rather than soybeans. So you're going to get your yield estimates, calculate your phosphorus removal by crop, total up to 2 years, and in most cases you're going to be making that manure application based on phosphorus. Okay, so let's say that you have 100 head of cattle, 100 steers, whatever, and you have they're putting out 8 pounds of manure per day, and so you got 800 pounds per day, and you total that up by 365 days, and then you would come up with a yearly annual amount of manure that you would have to deal with. And then as we begin to look at the phosphorus content of that, you would find out how much acreage, in conjunction with your phosphorus soil test, find out how much acreage you would need to spread that manure across. Okay. All right, so what you do is, again, look at the total number of animals in unit. I suppose they could give you a poultry example as well, turkeys, chickens, whatever. It's interesting, a little side note, I talked to someone who'd taken the exam, and they were sort of knocked out of whack a little bit in that they came up with odd animals or odd plants that they had not heard of, but you have to remember all of these approaches are the same. So, for instance, they could have ostrich manure and give you values that were associated with that, and you just go on, you just work with the numbers. So you look at the total number of animals, their daily output across a full year. There's a link in the objectives. We look at the learning objectives about ag waste and some different things to look at there. The necessity of a manure analysis is important. So again, analysis always is better than making assumptions, because it gives you a clearer idea of what you actually have. And you use record keeping to measure the annual amount of material that's going out on fields. So to find out whether you have enough land to actually dispose of this phosphorus and put it to good use in your agronomics, you need to evaluate what you have for fields. Some fields will be out based on setbacks from water sources and so forth, and then you may have high phosphorus in some fields where you're not going to be allowed to put manure either. So the manure management is controlled primarily by something called a phosphorus index. Iowa State's got something on this. Look at the manure nutrient content, and then what that is, and where it's placed, whether it's broadcast or incorporated, and what time it's put out within the cropping season. They use some of these variables to go ahead and construct a P index. And then once they go to this P index, there are different things that you can do and can't do. If you have a low phosphorus index, so phosphorus is not a limitation, you would tend to base your manure application solely on the nitrogen content and nitrogen source that manure would be. Greater than 2 up to 5, also you're going to base that manure application on the amount of nitrogen, again, taking account or credit for the amount of phosphorus that comes along with it, but do not exceed the, can't do application over 2 times the phosphorus crop removal. 5 to 10, you switch. So in other words, areas that have a high phosphorus index, so about halfway through this relative scale of 0 to 10, if you're in the upper half of that, you switch to a phosphorus-based manure application and try to reduce the amount of, reduce this phosphorus index through changes in some of your management strategy. And if you're above 10, you can't apply manure to those specific fields. Okay, so again, we're looking at crop removal recommendations, different strategies based on the analysis of your manure, whether it would be a nitrogen or phosphorus type approach. But keep in mind, again, for the general strategy of supplying nutrients for crops, you first, if you're using manure, you have to get that manure into the program before you start doing your other calculations. If you use fertilizer to meet all your nutrient needs, then come in with manure, you'll be way overboard on nitrogen and phosphorus. So if you got manure, get that in the calculation first. Okay, here'd be an example, just some stuff pulled out of some existing material on the web. And this, again, this includes an estimate of the losses that you might get in manure that's stockpiled. And there's really a lot of intricate literature on here, and I can't imagine they would hold you accountable for knowing all the nuances of that. But in general, if manure is stored or put on the soil surface, you have different amounts of availability. You lose some of it into the atmosphere through ammonia volatilization and so forth. So some of the estimates I've seen is that in general, some of your large mammal manure runs about 4% nitrogen, but you have about 36% of that lost to various nitrogen loss pathways before it gets onto the soil. So you get about 64% of it lost. So in general, if you've got stored stockpiled manure, it's generally going to run about 2.5% nitrogen. Okay. For phosphorus, I've seen much less loss, only about 5%. So you've got about 95% of that, and a stock value on that would be about 2.3. So about 2.23 actually percent P2O5 in the manure. Phosphorus and potassium are not extended into that second and third year calculation the way that nitrogen is. So that's something else to keep in mind. So hopefully you'll be given the tools and the constants and the data that you're going to need to look at this manure application. Okay, moving right along here, we'll talk a little bit about lime calculations. I'm not sure if they're involved in this particular exam, but you would get a soil test that would have a standard water pH measurement of your soil, and then also a buffer pH measurement of your soil. And the way that those two are different will determine the lime requirement to affect a certain pH change on your particular field. And so what would happen was they would say, for instance, that you would need the equivalent of, let's say, 2.3 tons of 100% limestone. Well, what they're using is 100% effective calcium carbonate, whatever, and you're going to make changes to that calculation based on the chemical content. In other words, if you have a calcium, magnesium, or dolomitic, some other source of lime, calcium oxide, burnt lime, whatever, you'll have a different equation there based on the molecular weight of that lime versus calcium carbonate. And also, it's going to be a little bit dependent on the fineness of grind that they determine by running this lime through nested sieves. So this is out of the Illinois Agronomy Handbook, and this is the efficiency factor for various limestone particles. So if you're looking at a year after application, if the limestone hangs up on an 8 mesh, which means 8 little wires per inch, then it's only about 5% effective. If it goes through the 8 but hangs up on a 30, it's 20% effective. Goes through a 30, hangs up on a 60, it's 50, and then anything that goes through that fine mesh is thought to be 100% effective. So then you'd come back into the calculation. This is a little bit small, but you take a look here, looking at the numbers that we just showed previously, you can see you multiply by the effectiveness, and then you tally up or sum up the total fineness efficiency, okay? In this case, 47.78%, and then you're going to divide that into the total amount of limestone that you need. So in this case, we had a calcium carbonate equivalent of 86.88, and this fineness efficiency thing of 47.78. Those both go into the final calculation, and you come up with an amount of limestone. So you can take a look at that particular calculation. I'm not sure the certainty of that popping up on this exam. Okay. All right, I'm going to end with a couple key points here. And as you can see, I'm well programmed to speak just about 50 minutes, which is a college class. But by way of review, let's talk a little bit about what's happening Tuesday for those of you that are interested. I'm going to spend a similar amount of time, and I'm going to try to go over all of the learning objectives and point to areas that I think would be prime areas for testing that would ask you to sort of involve and pull together a lot of different concepts working with different scenarios. But by way of review, we've talked about how do we do fertilizer calculations, how do we make conversions from English to SI units and back, how do we use different factors or ratios to eliminate a numerator or denominator in a fraction where we're trying to switch to a different, going for instance from pounds per acre to kilograms per hectare. We talked a little bit about how to construct an overall fertilizer approach. Remember, if you have manure, you've got to think about that first. You have to think about moving along the area of taking credits for manure if you have to use it, looking at the amount of P2O5 and K2O that you're going to export off that field based on expected yields for the next 2 years. We looked at a couple graphs that you may be asked to interpret how much nitrogen needs to be applied in certain scenarios, then use the correct source and placement and timing. We've looked at calculations with manure and how to approach a soil test and how to build up a soil test when it falls below that critical value. So with that, I'd say, Dan and others, if you've got questions at this time, that's pretty much what I've got for you. I'm hoping that all of you do well in the exam, and I'll be there kind of cheering for you. Additional resources you can look at, that IPNI manual I told you is pretty good, and good luck to all of you when we go into this exam here in a little bit. That's a picture of me up there, a little hard to see, of dominating the Jumbotron, cheering on the great Illini basketball team a couple weeks ago. That's what I have for you, folks. Go ahead, and if you have any questions, let me know.
Yes, Dr. Simmons, thank you very much for that good overview. Being a CCA in agronomist for many years, actually, and wanting to take the exam next August, I really appreciated that overview of touching upon many things that are pretty important to this exam and to CCAs. So we have a number of questions here to go over. Probably right now I got about 10.
Okay.
I'm going to read them to you.
Yep.
Is the 4-hour plant nutrition manual and sample questions of the exam? Is there a 4-hour plant nutrition manual and sample questions representative of the exam? And are there other objectives we need to or can research on Google?
Good question. I've found, and I've heard from actually a couple of successful test takers that that IPNI manual, I don't have it right here handy, but that one is a really good resource. I'd be happy to send this out to the powers that be to email out to people. I don't know if you can still get it in time for this exam, but there are questions, scenarios, and so forth in that, and I think that would be a pretty good source. In terms of practice exams, I'm not sure I've been able to find any.
On that, yes, on that IPNI manual, if you can just email a link to Ann Herrick, and she can just email that around. maybe you can buy it online and download it online. I'm not sure where they're at on that technology today. But you're right. They make very good manuals for these things because they're very practical and focused. On that, you talked about the maximum return to nitrogen, and you gave that curve up there. How does that curve kind of move, if you're planting corn after soybeans or you're planting corn after continuous corn after corn?
Yeah, good question. Almost always the curve shifts back to the left after soybean, meaning that you don't need as much nitrogen. And you can get on that website and play with that a little bit, and that's what I do for my intro crops class. But yeah, so basically almost all scenarios, if you're coming behind soybeans, you have typically need less nitrogen, and oftentimes the curve has a more clear inflection point.
So that in that model they run, that will pick that up and shifts that number around based on the previous crop.
It's a real user-friendly website. You just type that in and it'll pop up. It's free, and you're changing the variables you're changing is the previous crop, cost of nitrogen, and expected dollar return for a bushel of corn.
Okay, move on to the third question. Manure analysis reports ammonium nitrate and organic nitrogen. Is it the organic end that plays out over the 3 years, and the ammonia end that you take the first year?
Good question. If it's a straight soil test.
No, manure test.
Manure. Okay, this is manure. I'll
it's manure analysis.
Yep. So I'll start with manure first then. Manure, you've got the free ammonium that's in there and the free nitrate, and that's part of the first. That's immediately available. And in addition to that, some of that organic nitrogen is going to mineralize. So I think all of that together is going to give us the 50% of that total amount. But the ammonium and nitrate are going to be immediately available.
So when you look at that organic component, that's where that plays out. When you look at nitrogen over the second and third year, you can take a credit for that.
Right.
So of that organic component, how do you of that organic nitrogen and manure, do you split that sort of 3 years, 30% the first year, 30% the second, and the other 30% the third year? Is that how the math works?
No, it's like 50, 25, 10 as near as I can tell. And I'm going to try to look into that more. I may contact the people that wrote some of those things that I looked at. But yeah, generally you've got the biggest load up front, but the second and third year you're still mineralizing the organic portion of that manure for nitrogen. Phosphorus and potassium, not so much.
If you look into some things, Dale, you could just compile these and send them to Ann, and then she can circulate these back to the people that register for the van. Relating to the phosphorus and potassium rates, in this economic climate with lower commodity prices, would there ever be a question how you relate those nutrients to price of the commodity? Would that ever come up in the exam?
I would think not. In reality, I think if people are cutting corners, they're probably going to cut a little bit ahead of soybeans, and obviously they're not going to nitrogen's going to go out on corn. But I have not seen any algorithms that relate the price of P and K to application decisions. They are built into the maximum return to nitrogen.
Right. So there's none likely they won't have any questions on that.
That'd be my guess. That's my best guess. Yeah.
Could you one of the questions? Could you review again this critical and maintenance graph?
Sure.
Maybe you want to pop back to it in your presentation.
I'll see if I can do
and
that.
Just go over that.
Sure. Yeah, that's a pretty key deal. There we go. Okay. So here you've got a soil test that's going to reside somewhere on that lower axis from low to high. So this would be for phosphorus and potassium primarily. And there's going to be, for given soil situations, what's called a critical level, okay? And to get into more depth on this, I know in Illinois, it's related somewhat to the phosphorus supplying power of the subsoil, and potassium is related to the cation exchange capacity of the surface soil. So those values are known for a given situation. This is sort of a generic diagram here. So if your soil test is below the critical level, and we're looking here at anything from, I've drawn a little line here all the way to here, which would correspond from here to here on the soil test level. Anywhere in that area, there's going to be a difference between this point. Let's say this point is 40, just take some arbitrary numbers, and you're at 30. Okay? It's about like my regular handwriting. So you're trying to improve this 10 pounds per acre, and that's when you're going to need a buildup. So that, when you're calculating the total amount of fertilizer needed, let's say you're putting out phosphorus for a 2-year period. Your amount is going to have 2 components to it, the buildup component and the maintenance component. So you're basically fertilizing 2 things. You're fertilizing for the need of the 2 crops that are coming off that ground, and you're also fertilizing to bring that soil test up, so that hopefully the next time you soil test, you'll be up to that critical level and somewhere in the maintenance range. So what's the reason you want to do that? Why not just fertilize for the crop every year? It's primarily to protect against situations where you have ideal growth conditions and either phosphorus or potassium become a limiting factor. So then, as you go through the maintenance range, there'd be another value up here, and it would, who knows what the range of it would be, but there'd be another area up in here. Anything to the right of that on the soil test, so from here to here, you are not going to add fertilizer. So if your soil test is out right here somewhere, you are not going to need any of that fertilizer. Okay, I hope that provides some clarification.
Okay. Is alfalfa credit a standard credit, or will we have to make adjustments for the alfalfa stand prior to the corn crop?
Okay, we've got 2 things there, test taking and reality. In reality, they typically would provide you, like if you were doing this on your own, you would have access to tables. And yes, the contribution of alfalfa to nitrogen is related to the quality of the stand based on plants per square foot. So if they give you that, great. You should know how to work through a table like that. In the absence of that, so sort of a generic amount that I've seen over and over again through the years, it's about 100 pounds of nitrogen that comes from alfalfa the first year and about 50 the second. So that, I think it would be, you'd be protected by the Geneva Convention on Cruel and Unusual Punishment if you're asked to actually memorize the table for number of alfalfa plants per square feet. I could be wrong, but I think that's the case. So if you got a big stand of alfalfa, 100 pounds the first year.
And then you said it was 50 pounds the second year.
Yep.
Was in the presentation.
Yep. Soybeans 1 year only.
And soybeans only 1 year.
Yep.
Will we have to know the critical and other levels for P and K, or will they give us that in the exam?
Good question. I can't imagine that you would be asked to know them because they vary by soil. Some states may have a generic thing based on, but no, since this is a regional test, I can't imagine that you would be asked to know critical levels. Now, what if I was writing the exam for something like this? I would say, you have this soil, give it a name, and then the critical level for phosphorus is X, and the maintenance limit is Y, and your soil test is another number. And then you just have to know that you're below the critical level, you're above the critical level, below the maintenance limit, or you're above the maintenance limit. And all 3 of those scenarios would have a different approach.
Okay. How particular will it be on questions on how critical will it be on questions relating to the P index? Because not all states use this.
Right. I don't know. Again, I can just hypothesize that if they're going to give you anything about the P index, they would have to provide you with that P index and give you a chart to choose from. I think it'd be wise to know, and you're right, not all states use it. I think it'd be wise to know that if you have low phosphorus in the field in general, then you're going to use your manure application calculation based on phosphorus. And if you have ample phosphorus, then you're going to make it, look at the limitation of phosphorus and use that as your defining factor. That would be my guess.
Okay. Well, we have a lot of questions coming in here, Bill. If you're using MRTN, do you have to take manure and nitrogen credit in 2 and 3, in years 2 and 3?
Oh, wow. So let me think about this. So this would be with manure on the MRTN, right?
Right.
Right, okay. Yeah, I think you would. Sure, you still would. So let's say your MRTN comes out as 150 pounds N. You've got manure with X amount of nitrogen in it, 50% available. Next year you're going to soybeans, so you don't really care. But in that third year, I suppose you could have 10% of that nitrogen available for the corn that followed in rotation.
So you can legitimately take those credits as part of the MRTN in the second and third year.
Well, the second one wouldn't matter. Well, unless you're corn on corn, yeah, then it would matter, sure. So yeah, right. That would be good.
That's right.
Well, that'd be
corn, that's right.
That would really tie some concepts together, all right.
That's a good point, because that would be on a corn-on-corn situation. Of course, going into the soybeans, you won't worry about it. But that's a very good point. What is the subsequent crop? Next question, when you gave us the P and K amounts to raise soil test levels, do we have to add removal on top of that, or is it included?
Very good. Yeah, great question. Great question. I'm glad I've still got this graph up here. Okay, so again, let's look at this again. Everything to the left of the critical level, where it says build up soil, not only do you build up soil, but you also do the maintenance amount, okay? So to the left of critical level, you do the 9 and 4, do that calculation, but you also add to that the amount you're going to take for crop removal. If you're to the right of the critical level, but left of the maintenance limit, you are taking crop removal only. I bet some of these folks out there wouldn't mind if I put a couple of sample problems together. Do you think?
No, I don't. Yes, you're exactly right. Let's get more questions here. What is this? Would they expect people to know the difference between soil pH and buffer pH? In some states, they use buffer pH. Don't use that in Illinois. Will that throw people for a loop if they throw something out there about the two different pHs?
Well, I guess from my standpoint, and again, this is what I teach here at the University of Illinois, the knowledge of what the buffer pH means in comparison to the regular water measured pH. So the water measured pH tells you what your pH is. The buffer pH helps to determine a lime requirement to affect a change in pH to raise it above the level that you're currently at. So what this means is, basically, when you add this buffer solution, if there's a lot of acidity there, then the buffer takes care of that and doesn't change much. So buffer pH, if you get a big difference in that, it typically means that you've got an unbuffered situation. So what buffering means is, if you have a highly buffered soil, that means it takes more lime to affect a pH change than in a poorly buffered soil. So an example would be, let's say you have a sand with 0.5% organic matter, somewhere along a river margin or something, and a pH, 5.5, you want to raise it, and you've got a deep, dark 5% organic matter silty clay loam at 5.5, it's going to take way more lime to raise the pH in that silty clay loam. And the reason is there's so much cation exchange capacity that for the pH you're measuring in solution, there's a lot of what we call reserve acidity back on those exchange sites that needs to be dealt with as well.
Okay. In manure and biosolids, is there a difference in annual availability of an ammoniacal and an organic N?
Well, good question. I mean, biosolids usually anaerobically digested. I'll be honest with you, I don't know the exact conversions of those. That's something I could try to look into, but it's organic matter, and you would think the mineralization rate once it gets in the soil would be about similar.
Okay. This kind of relates to that graph again, and maybe you answered it in the previous question. How do you determine the soil test level when you only add maintenance application or no fertilizer at all? How do you determine the soil test level when you only add a maintenance application or no fertilizer at all?
Okay. Well, you're still soil testing at some point. So in other words, let's say that you soil test and all of your values are in what's called the maintenance range, right? So the soil's okay, it's not too high, it's not too low, but you're taking off nutrients. So in other words, you're still planning forward for what's happening. Now, that being said, in the real world, in many of the locations in the Corn Belt, it was hit or miss this year, but the last year, 2014 had some astronomical yields. So in fact, we probably took more P and K off of those fields. But again, you're looking forward, not backward, when you were using the maintenance amounts of fertilizer application.
Okay. Gypsum I'm just going to move through a couple more questions here, Bill.
Sure.
Gypsum is being marketed as a source of sulfur, a soil amendment, and trapping phosphorus. Can we expect any questions on this?
Don't know for sure. I'll just make a couple comments. I mean, gypsum is a source of sulfur, obviously, and in some cases it can improve soil structure, especially if you have cation exchange sites in some of our a little more less rainfall type areas that maybe have some sodium on the exchange site. But the tying up phosphorus, I guess in theory, if you've got a high calcium content in direct contact with phosphorus, that it can form some calcium phosphate type things. But gypsum is pH neutral, so you shouldn't be having a change in pH that occurs with that.
Okay, in an example next question. In the example you presented in the handout from Lisa, please clarify the text indicating if K levels are less than 260 pounds per acre on a low EC soil, the maintenance fertilizer amount should be multiplied by 1.5. Okay.
Yeah, that's a caveat of actually the state of Illinois and the Illinois Agronomy Handbook. So I don't know if that's a general testing. It's kind of like the P-index that Iowa uses. That's just information that I had that I use in class. And in that particular case, you have to up it because there's some reason in that case that the K level is so low. There may be fixation issues or other things. So that's just a trial and error deal. That's one small change to the general idea. But I think I'm going to go out on a limb and say something like that is too specific to a region and a state and wouldn't be good fodder for a regional exam like this.
If you had a manure analysis of 50, 25, 10, I'm reading your question.
Okay.
50, 25, 10, does that 50 represent just organic N, or is it total N? What does that 50 value represent?
Yeah, key note on this, pay close attention to this answer, because that's actually percent that's available. It's not a analysis. The analysis would be more like 4, 2.2, and 5 maybe on potassium. So what that is the percent available in each of the 3 successive years.
So that 50, 25, 10. So that's 50 the first year, 25 the second, 10. That's what's available over the 3 years. That's just the organic components?
Yes, that's the nitrogen out of the, it's the availability of nitrogen.
Okay. I just had another question. I had a question, and then I asked you to clarify that, or I forgot what it was. Will there be questions related to some of these stabilizer products on nitrogen, on phosphorus to keep them available, on nitrogen to keep it available? Will they have questions related to that?
No, they could. I mean, I think it would be wise to know some of the totally accepted scientific stuff out there right now that wouldn't get them in a position where they had to defend something, but there's obviously a need for urease enzyme inhibitors, when surface applied urea or UAN. Okay, you need something like that there. If it's knifed in or watered in, not so much. And then, of course, nitrification inhibitors for fall applications. And keep in mind your temperatures, both air and soil that you're working with for those kinds of things. So I think those would be the 2 big things that would be possible. I think you can also perhaps look at a urease enzyme inhibitor in manure that's surface applied as well.
Okay. Well, Bill, that's all the questions we have right now for today's event. If the people participating today, if you're going to come online again on Tuesday for Bill's presentation, go ahead and start compiling your questions. And that's your last opportunity for the exam to ask the expert to make sure you understand all the principles. Any other types of advice or recommendations you have for the listeners today, Bill, to take that exam?
Well, again, I mean, just general test-taking strategy, the best thing to do is to be rested and keep your mind open on scenario thinking. A lot of what I'll try to do Tuesday is to, sort of try to outthink the question writers and just think about things that people who do education in these areas, that keep things that people really want you to remember. So the stewardship of the manure, the credits, what soils can use what nitrogen sources. That's some of the stuff that I'll be spending some time with on Tuesday. Okay.
Well, we'll bring this to a close now. First, I want to thank you, Dr. Simmons, for spending the time today to do this webinar. Very, very educational, very informative, very good review of a lot of good principles. And we look forward to your presentation next Tuesday. On behalf of the Illinois Soybean Association, I'd like to thank all the listeners today for participating. And as I said in the beginning, this presentation will be up on the Illinois Advisor website by the end of the day tomorrow. You can listen to it again and review some of those principles for the exam. And as a CCA, when you registered, you submitted your number, and you'll get 1 credit in nutrient management for this participating today. And if you listen to the recording, you can go on the CCA website, log in, and you can apply for 1 CEU, just self-apply. Again, thank you very much for participating today, and thank you, Bill, for your work on this. And we'll all reconvene again next Tuesday morning at the same time.